that. Thanks.
Okay, thanks, Tony. And first of all, I just have to say, wow, those 3 presentations, very different, very insightful, and I actually don't envy I'm not happy about being on the transition from AI to something else. So what I do want to do is actually pave that transition by highlighting a few things. What I'm going to be doing is not explaining quantum computing to quantum scientists because we have them here in the room, and I think you guys kind of know this stuff. What I'm going to try to do is provide metaphors for understanding what kinds of problems work well with quantum computing, which are not necessarily the same problems that work well with AI, although they work together. And to explain what I mean by that, I'm going to talk about what we've been hearing in great detail in the previous 3 presentations was essentially that LLMs, AI in general, but more specifically LLMs, are great at pattern matching. They're fantastic at picking up patterns that humans will not pick up. They're really good at it. The problem, as we heard particularly in the last one, was, well, you know, pattern matching can be great when there's actually a pattern there, but sometimes it can generate truthiness instead of truth. Thank you, Stephen Colbert. And the classic example of pattern matching that is bad pattern matching is Elizabeth Holmes, if you guys are familiar with her. So she's one of those people that went out and she checked all the boxes. She, you know, dropped out of Stanford. She wore a black turtleneck like Steve Jobs. She spoke in a funny voice. She got lots of celebrities on her board, and her company was a complete and total fraud. It was Cargo Cult. But it matched the patterns, so this company, Theranos, was worth more than practically any company in the world for a little while, because she matched the patterns so well that nobody could go back and say, well, actually, this makes no sense because. Now, it did make no sense because anyone in that field could point to it, and that's an important point too. Anyone in that field could point to it and say, hang on, no, that's not actually possible to extract that much information out of 2 molecules of blood or whatever. But the problem was so many people got fooled, and they got fooled in exactly the same dimensions that led to Apple and Google. And people said, well, all these things you throw at her would be complaints about Apple and Google, and yet, you know, they turned out to be great companies with, you know, great value. Point being that matching patterns is a double-edged sword. So as I love the way Gideon really focused on, yes, you're going to have to build in a mechanism for validating the actual truthfulness of the output, and proposed one that I thought was simple, elegant, and incredibly functional. That leads to one last observation on AI before we get to quantum and the problems it solves well. So the last observation there is, I loved Paul's discussion of putting all this in the broader context of history. And all I could think of was, you know, LLMs in particular remind me a hell of a lot of outsourcing. Because remember when everybody wanted to outsource because you were going to reduce headcount. You're going to hand everything offshore, and then all those people offshore would do it, and you didn't need very many people. And what they found out was they were actually just reducing engineering headcount, but building up project management headcount. And so it was a wash in the end. You needed, well, not quite, because the project managers were not necessarily as expensive as the engineers. The point is, with LLMs, what you're really doing is shifting the burden to the subject matter experts. Or as I was talking, you know, because of this need for validation. And I was talking to someone about it last week who was using LLMs in his job, and he said, look, we thought we were going to be able to fire all the writers, and we did, but now we had to hire all the editors, and the editors are more expensive than the writers. So getting back to that question of what do you want your kids to study, I would strongly suggest that they get subject matter expertise in something, because they're going to be the highly paid editors who are validating the output of Gideon's algorithms to make sure that they actually make any sense. Now, if you've been following along, you're going, okay, that's kind of a real simplification of everything that we heard, which is very true. And that's kind of what I'm about to share with you in the area of quantum. So switching, what are the problems that quantum actually does well? Don't take it from me, take it from David Deutsch, who is actually the father of quantum computing. He's the guy that was running around in the 1980s going, hang on, I bet you could use this stuff for computing. Coincidentally, at the time in the 1980s, I was like many of you, an engineering undergrad. I just took a weird turn in my career because I decided I really wanted to be a particle physicist. So I went to grad school for particle physics and discovered midstream that although I love research, I really, really, really hate academia. So my hat is off to all of you guys who have survived and thrived through academia, because the world is a better place because of you. I couldn't hack it and dropped out. And for many, many years, I had to sort of say, okay, my little particle physics thing was great fun, but it was a detour. And now with quantum computing, they're coming back together. But now that you've had time to read and absorb that quote, think about it for a second. The first technology that allows useful tasks to be performed in collaboration between parallel universes. So the thesis I'm going to propose to you is, if you buy my argument that LLMs are pattern matching with lots and lots and lots of simplification behind that, quantum computing is essentially parallel instantiations of things and fuzzy optimization. And I'm going to drive that through and see where we go with this, because it'll start to get a lot more practical. Yeah. Okay. For those of you, for some of you, this is so basic it's ridiculous. For those of you who aren't quantum scientists, basically the fundamental concept is you've got qubits that have multiple states, which are not necessarily binary. And kind of this is a metaphor. This is not exact science, but the way that a lot of people who've come up through computer science can understand qubits is, if you think about the great insight in computer science is, oh well actually in electrical engineering is, oh, we can basically do binary calculations, which can do everything that decimal calculations can do, just a bit more complicated, but reduce it down to on or off, and each state can be just one thing or the other. Quantum goes in the exact opposite direction and says, well, let's take decimal, just say if you had decimal, for example, and for each decimal place, that could be anywhere in the real numbers. So right now, it can be 0.1 or 0.2 or 0.3, but what if it could be anything? It could be point I or point, pi or point any number. So now you get this dimensional spectrum of blurriness for each decimal place. It doesn't have to be decimal, but I'm using it because it's familiar. And you go, oh, it's the exact opposite of what we've been doing with binary. We take best decimal and turn it into binary, simplify the states to 0 and 1. And with quantum, you're essentially complexifying them infinitely, which is why it becomes such a good way to look at organic and natural problems, which aren't really digitized. Because when you think about it, mathematics digitizes stuff, our conventional mathematics digitizes stuff in a way that the real world really isn't, the organic world isn't. Essentially, because a quantum particle is actually existing in many states at the same time, it's sort of the same as your transistor being off and on, or maybe a little off and a lot on, or maybe 40% on and 60% off and a little weird. So that's that whole each digit being any real number, and therefore you're getting more information, but it's also much noisier information thanks to things like the fact that when you're reading it, you can change its state, and it's also, entanglement is a huge problem, as we'll talk about in a little bit, before we get to the things for which entanglement is a solution. And what I mean by that is each state is not existing independently. It's actually entangled with its neighbor and other states, other qubits, and it's, when you're reading it, it may give you the wrong value because it was entangled with something that you didn't want to be looking at. And the reason I'm stressing this is because IBM recently this week came out with a really cool fix that I love. And it was actually suggested by an intern, which I also love, which is very fun. And then there's quantum entanglement, which all by itself can be very interesting, and I'll show a couple examples of that. My professional background is in networking, so there are a couple different applications of quantum computing to networking, but one of them is entanglement to exchange key information, which suddenly becomes hyper secure. And most of you sitting here have read that, oh gee, quantum will break cryptography and anything that depends on cryptography, like blockchain, which is true. It's absolutely true, and it's even truer today than it was 3 months ago. However, it also has the seeds of being more secure. You just have to change absolutely everything. And we'll get there, because what fun is that if you just incrementally improve? Okay. So, kind of the big themes. Information processing density can break through Moore's law. That's an older theme, and I'm not sure it's as true as much anymore because you're seeing lots of other ways to break through. Optical computing is one of them. So it's interesting, but I wouldn't say it's the most important here. I mentioned it can break many conventional cryptographic systems, but it can also create more secure systems. You can speed up things like search, but most importantly, the last two bullets are really key. Quantum entanglement brings in this whole notion of information at a distance, and we're only beginning to scratch the surface of what that means. I wish I'd been here for the speaker who was at the CIA, but you can only imagine what the CIA wants to do with that. You don't really have to imagine. And I just mentioned another application, which is secured key exchange, uncrackable key exchange. There's also the fact that quantum computing and AI together are very copacetic, because AI solves a whole bunch of problems that quantum computing is actually bad at, and vice versa. So when you apply them, you can solve certain practical problems much faster, and I'll give you an example. So what have people done to date? We do kind of a survey here. So the big one was you can split a task between existing or near-term quantum devices and then classical computers. So you're kind of saying, okay, things that basically sheer number crunching do well, let's have that running on a classical computer, and then let's see what we can do with these preliminary 100-qubit kinds of machines. And by the way, as I'll mention shortly, I think we're in the dozens to hundreds of qubits. Intel just announced that it's producing, I think, a 12-qubit chip, which is actually a very big deal because Intel is mainstream. I know the Intel folks may be here, and it's actually a really, it's a red letter day that they're doing this. Goldman Sachs partnered with Honeywell, which actually bought Cambridge Quantum and renamed it something I can't quite pronounce. I think it's Quantinuum. And it does things like exploiting variational algorithms for stock and option prices. Those of you who work in finance can immediately go, oh yeah, I can see that. What I find interesting is, with my particle physics background, Cambridge actually developed an algorithm that speeds up Monte Carlo enormously. And this is a really, really big deal because we use Monte Carlos for a lot of things. And for those of you who aren't familiar with it, Monte Carlo simulation is basically sort of spraying out a whole range of probabilistic things to test. In my case, we were trying to figure out where to put the detectors for particle physics experiments, but you can use it for all sorts of things. It's a way to test out scenarios. And that kind of gets us to what quantum computing is incredibly good at. As you can see, we use it in risk analysis, for supply chain logistics, for any kinds of optimization problems, try to figure out the best way to do something. So the fact that you can speed up Monte Carlos is right then and there a really useful application of quantum, but it's not the most. All right, now we're going to do a little memory lane to those of us who studied computer science. First, I'll talk a little bit about the machines, and then we'll talk a little bit about the known state of problems and then new problems. So, key point, when I was preparing this talk, the TTI Vanguard folks said, this is great, you want to talk about quantum computing, but is it really real? I mean, we've been talking about it for years and years and years. Yes, it's real. Yes, you can buy it. Yes, you can buy it that does different interesting things. What is the it? Computational machines, networking machines, like commercial entanglement-based networking is here and running in networks, which is actually quite interesting. As well as a lot of interesting software, because as you've heard from the previous three talks, when you have a whole new paradigm for doing something, you actually need a whole new software toolkit, and that's one of the things that's coming along with quantum computing. As I mentioned, the qubit count is low and noisy, but the rate of improvement is really fast. So we're going from, call it 100 qubits to 4,000 qubits in 18 months. And by the way, IBM's solution for noisiness is, again, good, and I'm not surprised it came from them. And again, you can get languages, you can get open source languages, you can get cloud-based simulators, you can go spend lots of money on it, or you can go spend no money at all. But if your question is, should I have a quantum computing team? And if so, what would they do and how much would it cost? You can get their feet wet if you want to use open source and the cloud, some of the cloud-based tools before you go out and shell out, tens of millions or hundreds of millions for machines, which also exist. Okay, so this is the fun part because probably about a half to 3/4 of the room remembers this. but sort of vaguely. And I will admit I had to go brush up on this when I was starting to look at the types of problems that can be solved. That plus the proof of Gödel's theorem was a lot of fun last fall. Anyway, a p-algorithm is an algorithm that can be solved and the solution verified in polynomial time. So a p-algorithm is pretty much anything that basic classical computing can do well. Number crunching, P is number crunching. The faster you crunch the numbers, the faster you get the answer. We're done here. An NP problem is one for which, if there's a solution found, how do you verify that solution, and can you do that in polynomial time? So the classic one is prime factorization underpinning RSA encryption. Guess what? That's one of the ones that quantum can break. Now we get into NP-complete, which are problems that can get converted in polynomial time into each other. So any NP-complete problem is any other NP-complete problem. And actually, there is a Simpsons episode of all things where that's on the blackboard. and yeah, that was just, I was like, that can't be right. Went back and watched it. It really was. And then there's NP hard problems like the traveling salesman, which is, for those of you who don't remember it, or for those of you who work in sales and are like, that sounds interesting. Let's say you have to visit every single city in the country, or every single city above a certain size. What is the optimal route so you visit each one once and only once? And you look at that and you say, oh, that's an easy problem. And then you get deep into it and you realize it's actually not even a solvable problem, or barely solvable. But that starts to give you a little kind of clue as to the kinds of problems that quantum solves well. Because at the back of your head, you may be thinking to yourself, you know, I don't actually have to visit each city once and only once. Like if I only visited a couple cities a couple times, that would be okay. Like if they were big cities or cities where I could do something fun. And then you start to realize that there's a whole level of optimization that says, good enough. If I don't have to have the one perfect route, but a route that's pretty reasonable and I can set parameters on that reasonableness arbitrarily well, then that becomes very useful. And in fact, this is where you fall into things like BPP, which is bounded error probabilistic polynomial time for classic, and BQP, which is bounded quantum polynomial for quantum. And the idea is, I need to get a solution that's good enough by a good enough definition of good enough. So computers can generate an answer in polynomial time that's highly likely to be verifiably correct, but not necessarily verifiably correct, but close enough. And so you can basically take a lot of these problems into the category of I can solve them if I'm allowed to say what good enough is. And if you think back to Monte Carlo simulations, again, it's not particularly exact. So the idea is you're sitting here thinking, okay, if it's close enough, it's good enough. And then you realize there are an awful lot of problems in the real world that are of that sort. And quantum allows you to do that by, remember the parallel universes? If you essentially say, I'm looking at all possible solutions to a problem, maybe not all possible, but most solutions to a problem. Okay, let's fuzzy. Most solutions to a problem, and I can see which ones are reasonably good and which ones are horrible. That actually solves a lot of real world problems in ways that we have not even been able to address because it's not mechanistic. And I'll get into that a little bit more. Now, I mentioned quantum plus AI. So I have a Nemertes advisory that I put out once a week, and back at the beginning of the year, the big news was some researchers in China claimed that they had broken cryptography with quantum computing. Turned out they not only lied, but they lied kind of egregiously because they leveraged the two different algorithms that sound like each other and have nothing to do with each other, Schnorr's algorithm and Shor's algorithm, and don't get me started on this. They essentially came to the conclusion that it is breakable and will be breakable, but we haven't broken it yet. So people got all in this uproar for a couple of months and then realized it wasn't. However, right after that happened, so I sent a nice little advisory like, relax, don't get so uptight, it hasn't been broken yet. Then the freaking Swedes did it with this, they actually attacked the NIST recommended quantum hardened encryption algorithm. And what they actually did was they used quantum computing, but they also had recursive training AI that was sitting there doing its thing, pattern matching. And it was noticing, oh, check this out. The power consumption surges when computation is crunching and shrinks when it's not. And it was like, oh, that out of band look at the real world using AI blew it. And so NIST back in July was like, here we have these super hardened best minds in cryptography worldwide produce quantum resistant algorithms, and yeah, the Swedes broke it, and still, actually I haven't checked back, but when it happened, they had nothing to say. And my main point is that the best minds in cryptography didn't think of this, but should have thought of this. And so that's an example of quantum and AI each doing their separate things, using them to check and balance the other, which is part of the reason, and I'm glad to see you're nodding, it's part of the reason that I'm so interested in asking and answering the question, how do you know the output of an AI is true? Because if you can use quantum to validate AI and AI to validate quantum, now we're cooking with gas. So this one is quantum entanglement. This was way back in 2014. Researchers developed this new imaging technique that shines a beam of photons on an object, but then has a totally different beam that never saw the object that makes a picture of it. And there's the photo of it. And you're probably wondering why I went to the trouble of putting a picture of the photographer up there, because she's not just the photographer, that is actually the quantum scientist who did this, which brings me to a small but important point, which is quantum scientists don't always look the way you expect them to. Sometimes they're really beautiful women with great taste in hats, and in fact, if you look over there, we have a quantum scientist, beautiful woman, Skylar, wave. She already knew I was gonna do this, so I'm not embarrassing her. She works as a quantum scientist at BP. Point being, just to remind everybody that the world is a bigger and more diverse and interesting place than we may have our little frameworks, which is hopefully the big takeaway from all of the talks today. It seems like I'm kind of winding down the talk, but I'm really not, because we're just getting to some of the good stuff. So what is quantum good for? Problems that need not be verifiably solved. So anything that can be a BQP problem with a wide range of simulations. So you can say, if I don't need to know what the optimal solution is, but I need something that's an acceptably optimal solution with a set of parameters that I can arbitrarily tighten up to a point, that actually encompasses a whole lot. NP problems and NP hard problems can be not necessarily solved, but improved enormously, particularly if you can get outside hints from things like AI or looking at the physical world around there. And of course, entanglement gives you this ability to connect at a distance to do all sorts of interesting things. I want to highlight something when I talk about sort of squeezing things down to an arbitrary level of precision. Some of you may be thinking, hang on, isn't there a principle in quantum that says you can't actually do that? And what you're thinking of is the Heisenberg uncertainty principle, which basically says you can know a particle's position or momentum to an arbitrarily tight degree, but the tighter you squeeze on one, the less tight the other is. It was actually a culmination, like a really wonderful moment in my life, when I realized that the Heisenberg uncertainty principle is simply physics applied to Fourier transforms, which most of us in computer science know about. Because there's actually a fundamental principle, mathematical principle, having nothing to do with physics or momentum or position or anything else, which is any non-zero function and its Fourier transform can't be localized past a certain degree of accuracy. You just can't do it, and you can prove mathematically that this is the case. And interestingly enough, people are still in the process of proving it, even though it's known. And while I was refreshing my memory on this, I actually read a 2021 paper that was one of the most elegant proofs I've ever seen, which is actually really, really cool. But the point is, if you just say, oh, well, the Heisenberg uncertainty principle is simply an application of Fourier analysis, and you just insert position and momentum for the function and its Fourier transform, because momentum is, I think I've got it the right direction, but the waveform of momentum is the Fourier transform, the waveform of position. Boom. So this is a fundamental mathematical thing that has nothing to do with quantum other than it just happens to be applied to quantum. So it's a key to thinking about the kinds of problems that quantum is good for, though, because taking a big step back for a second, if you go all the way back to the turn of the last century, there were lots of noises and rumors that we'd figured pretty much everything out about physics, and it was all super mechanistic. And people had these mental models. Paul's pictures were great. These mental models of gears and camshafts and things like that, and that's really what physics was in their heads. And you'll have noticed that in conventional culture, we talk about software and hardware, and we're using models from information systems, which came along 3 generations later. But the point is, we had this very mechanistic model, and everybody sort of thought in this mechanistic model, and our brains were sort of acclimatized to the idea of thinking, well, you push here and then this results, and if I just simply sum up all the possible results, I have the explanation of absolutely everything. And so therefore physics is over. That's actually what they said until they suddenly discovered quantum. And the thing is, people took quantum, and partly because of Einstein's incredible personality and youth and everything else, they sort of put it on the shelf as, okay, the universe is mostly sane, but there's this quantum aspect that we just don't talk about, and shut the shelf. And the whole fact that the Heisenberg uncertainty principle is a direct outcome of Fourier analysis, and Fourier analysis is core to anything with signals and systems and communication. Yeah, no, quantum is built into absolutely everything. That model where it lives in a box by itself, you can't use it. And just a quick side note, when I was, one of my friends in graduate school was actually doing quantum chemistry, and her entire thesis was modeling, I can't remember whether it was the hydrogen atom or the helium atom, using very quantum mechanics, but very mechanistic kinds of models. And I'm thinking, boy, her entire career has just changed with the advent of quantum computing, because now she can model it the way it needs to be modeled. But again, the goal, the reason I brought up the mechanistic approach to things is, at the back of your head, there's this idea that there's a right way to do something, and that you follow the right steps. It's not a recipe, but it kind of is, and you get to the right way. And quantum breaks that, but it has a sort of inherent truthfulness to it, because we know in the real world that there's no one right thing most of the time. And so the idea that there's many ways to get there, and some are better than others, and some have absolutely awful outcomes, and some have pretty good outcomes, those are the sorts of problems that get opened up to us with quantum computing. So what are these sorts of problems? Well, those of you who work in finance are already going, gosh, anything we're doing modeling and simulation, weather prediction, large system simulation, if I had to guess, Skylar, I'd be imagining that you're doing quite a lot of that, because that's what you do in oil and gas. That's certainly one. Reducing network complexity is another one. I haven't seen anyone start doing it, but I expect it, because those of us who are familiar with routers, essentially you're sitting there and you've got a very stupid static route table that says, to get from A to B, I forward the packet this way. And if something changes and I change my routing algorithm stays, but if the output of the routing algorithm is something different, okay, I'll just download my new table and forward the packets in the other direction. Well, that makes no sense actually at all. It is the most primitive thing you've ever heard of. And if you had little quantum computers at every router that could simply see, I mean, when I say see, quotes, but knew all the possible outcomes of sending a packet any possible list of ways across the network, it would loosely optimize, because if you think about policy-based routing or things like that, oh gee, I want to send the packet in such a way that it doesn't go into my enemy's hands, gets there within a finite latency barrier, gets there with an X or Y degree of validity, so it's actually that packet. Now show me all the different routes and pick the right one, and do that all really fast so that it all happens. That's a much more sane way to do routing than our current one, which is literally, I got a checklist, you go there. Okay, wait, no, just got my updated checklist, you go there. The example of I think somebody said earlier, if my doctor is still faxing my medical forms, it's almost that. Policy hardening. I love this one, because you say, what's a policy? Well, I do a lot in cybersecurity. So you have a cybersecurity policy that says, people ought to be able to do no more than they should be allowed to do. And devices should be accessible to only this subset of people, which, by the way, as you start getting into it, you try to build out a policy on Excel, and you realize the thing breaks, and you're like, okay, maybe I need a database. And then that breaks because you're clustering things differently, and you're like, oh gosh, there's no possible way to say all the things you want to say in a policy. Well, with quantum computing, you can simply say, okay, what's the impact of Johna getting access to this? What's the impact of Johna not getting access to this? What's the impact of Johna getting access to this but not that? And let's do all those analyses in parallel and come out with a set of policies that will be good enough for your cybersecurity. That's huge. That is a really big one. Now, it may not generate, again, it's not going to generate the optimal policy because there's no such thing. But it can generate a policy that delivers on the parameters you put around it, which are make it good enough that it does this and that, but not this other thing. So you may say your policy is never, ever, ever have anyone outside the company have access to, the Coke recipe or whatever it is. Okay, but that might end up requiring, humans to come into the office and go into a locked room or whatever it is. Maybe not highly practical, but again, you can tell it what you want. I'm going to jump down to that second from last bullet because now you can start saying things like, oh, I would like to know whether or not sending this particular diplomat to this particular country at this particular time increases or decreases my chance of starting a war. Or in fact, how bad the war is going to be. So if I send John and not Johna, or I don't send anybody, what are all the different options? Which ones lead to the war? Which ones lead to a conventional war but not a nuclear war? Which ones lead to a nuclear war and the end of life as we know it? And which ones end to better trading deals? Just tell me all that. That's a form of policy hardening. And when I was talking to some of the folks on Wall Street, because I work with the Wall Street Technology Association, I just sort of mentioned that policy hardening generally is a great problem for quantum. I just got this, oh, you just rocked my world. And I have not even begun to get deep in that, but you can start thinking about how that works. Prioritization problems, and this looks kind of silly in the context of everything I just said, but it's not really, because like in the previous, when Gideon said we're going to have bit rot and it's going to be this problem. Well, if you've got like this enormous mess, the first thing you want to know when you're trying to fix it is what should I fix first? And you're able to, it's a subset of policy hardening in a sense, because you say, what happens if I prioritize this over that versus that over this, et cetera, et cetera. We talked about breaking blockchain and encryption. That's a done deal as far as I'm concerned. It hasn't happened yet meaningfully, but it will. And that's why we're looking at things like quantum resistant ledgers and in the long run, entanglement. And that gives us that secure cryptography. All right, now I'm going to spend a bunch of time on some really boring slides. Just a couple here, and I know we have some companies here who are actually presenting. I think PSI Quantum is here. Aliro Quantum is the company I talked about that does entanglement-based networking. They're very interesting, and most interesting is that they actually have customers, network companies up and running who are offering secure cryptography as a service and not secure key transfer, key exchange, which is different. They're actually entanglement-based key exchange, which is very, very different. Amazon, you can go look up what they have. You can get their stuff. D-Wave has a quantum annealing computer. Google has a whole lot of stuff, particularly with the AI intersection with quantum. Honeywell, that's it. Continuum, I still can't say it. These are the guys that speed up Monte Carlo simulations quite a bit. IonQ, which is trapped ion quantum computing. IQM, which I think they're interesting because they're a Danish company. They basically said, we can't solve all problems everywhere yet. So they're kind of doing the BlackBerry of quantum computing. It's like, I'm just going to focus on this problem of email. Mobile email is the problem I'm solving. So they pick very specific problems and then have machines that are designed to solve those problems. Over time, they won't be necessary. We'll have generalist machines, but we're not there yet. Microsoft, PSI Quantum, I'll let them tell you what they do because they have a great presentation. QCware is enterprise quantum software and services. QConnect, quantum networking hardware. And then the guys at the bottom, StrangeWorks. These guys are interesting if only because the company the leader of the company is one of those people that I call an aggressive iconoclast. I forget the guy's name, but he's one of these people. He had a high school degree, ended up being an Apple engineer, ended up as a managing director at Goldman Sachs, and then did a bunch of other things. And if you go look up his resume, he's very proud to say, education, none. And he's got this company that delivers, and it's in Austin, so also Texas, always home of aggressive iconoclasts. Then this I am so psyched to share with you. The first one is, like, if you're excited by all this and you want to go do something about it, IEEE is having Quantum Week. So those of you who are familiar with the IEEE, they were kind of quiescent during the entire IP revolution because basically the IETF kind of stole their thunder by creating IP and all of its ancillary stuff, but they have more than made up for it by jumping on quantum. So they're having Quantum Week in Seattle. It looks really fun. I urge you to all consider it. There's cotton candy and corn dogs, at least as I understand it. Okay, maybe I'm not sure about the corn dogs, but I'm sure there's cotton candy. I mentioned Intel's 12-qubit chip that just came out in June. With all due respect to the people from Intel here, I am not insulting you to saying this, but it's kind of like Subaru coming out with something versus Tesla. It's, instead of being very obscure and way out there, this is a mainstream semiconductor company with a mainstream product in this space, which more than anything puts the stamp of approval on it. I mentioned, the Swedish university, I was talking about all the tools that are out there. They have open source quantum computing software, so if you want to get involved without spending any money at all, go do that. The error mitigation from IBM, I promised you I would tell you, and we're getting close to the end of this. So basically what they did, they took a look at the noise they were generating with their qubits. And, you know how they did this? This is so cool. They looked at the noise and they said, well, there's just such a low level of noise, it's really hard to extract it from the signal. And so the intern's like, so why don't we amplify it? So they did. So they amplified the noise and they ran enough simulations so they could tell the noise apart from the signal and extracted it. And it really works. And they tested it against a classical computer. So it was one of these things where you could do a movie on this. Because the researchers walked in the door and they were like, they weren't sure which one was going to win. And the quantum computer won. And I just love it because it's such an elegant approach. Like, make the error big so we can see it. And that was great. And that's the big news from last week in quantum. But there will be big news next week. Amazon has artificial diamonds for use in quantum computing. I just love the fact that diamonds are a network's best friend. And then Quantinuum, remember Honeywell, Quantinuum, they have actually announced quantum hardened key enhancement. So that's kind of I won't call it a stopgap measure, it's more than that. But it does allow you to keep using your traditional classical keys in cryptography for a little while longer, which is a good thing, because we don't want all of that stuff to collapse while we're paying attention to this. So that pretty much wraps up where we are. I will jump through. This is just fun stuff. It's far from comprehensive. Internally, we have an internal store where when one of us finds something interesting, we upload things, and this is just a quick snapshot. You will get the slides, and the links should work in the slides because we've tested them, and they all go to where they should go. I would say of all of this, I think some of the stuff towards the end is actually pretty interesting. Apologies for listing Wikipedia, but it's actually quite good. This is just if you want to join with us and come talk about this stuff. That's our community. You can go hit the website and see community. This is us. I won't bore you with it, and that's where you can reach me. If you want to be on the advisory, they go out, as I said, weekly, more or less, sometimes fortnightly if I get busy. And they usually highlight things on AI, quantum, or something else of interest. And with that, I think I'm flat out of time. Indeed. Thanks. And I didn't get any questions, guys. What is wrong with you? I was sitting there asking questions.
Okay, there's a question, middle, second back row.
Hi, thank you for that presentation, Johna. Very interesting. I just had a question with respect to cost. I don't know if it's the case today, but I'm assuming going from the optimal solution to an acceptably optimal solution with quantum will eventually take a lot less time and hopefully cost less. Am I correct? or am I
No.
not?
What the inherent in quantum is you probably can't get to the optimal solution except for the kinds of problems it solves. So I mean, it's not true that quantum will never be able to give you optimal solutions, but you have to, broadly speaking, it's not like you can get 90% to 99% and then you spend $1 trillion and get to 100%. It's like now it has to be a problem that you're okay with 99.9 or 99.99. And I don't know that the cost necessarily goes up. It may be a function of time and scope and scale as well.
Okay.
Somebody over
Jim?
there.
Yeah, Jim, there's a mic behind you.
Yeah,
Well, okay, I'm not just going to yell.
you can yell.
So I know we're going to have some talks later about languages and tools and things like that, but I wonder if you could say a few words. You know, you were talking about sets of applications, but at the moment, pretty much each of the different models you talked about has a whole different way you program it, approach it, et cetera. And how do you see that kind of, you know, we've just had the whole morning of, gee, we don't know how to create software, and now we have a whole afternoon of, gee, we don't know how to create quantum software.
Bingo. And actually, I took the slide out, but we do have a recommendation for our clients, which is don't pick winners. We have no idea which one's the best, so, you know, if you want the recommendation, of course, money is no object, so go ahead and start a quantum center of excellence if you think you have problems that might be addressed, and get your people up to speed on all the big ones, and then make a decision in a year or 2 or 3, because we can't pick a winner at this point. We're sort of in the pre-ChatGPT era with quantum, so.
Okay, Christoph, second row.
Yeah, right in front of you. One application you didn't mention, how about finally a reliable weather forecast?
How about what?
A reliable weather forecast.
Actually, there was a slide in here that said that, and I took it out because it was like, oh, this is such a traditional tropey, but it's true. You might literally be able to say things like, gosh, it's going to rain. In my house, it sometimes rains in the backyard and not in the front yard, and I could get that. It'll rain in the backyard at 12:01, and that rain will hit the front yard at 12:02. And it might be off by a little bit, but I'm okay, you know, within a little, you know, it's 12:01 or 12:02, I don't really care. So yes, we will actually be able to get weather forecasting, which of course, for those of you who are doing anything pertaining to the weather, like, you know, like financial models, is a very big deal. So.
Okay.
Okay, I think I have to go.
Johna, thank you very much.
Thanks.